Hello everyone, welcome to Dr. Ravi's Academy. In today's virtual class, you will be learning one of the very important derivation of strength of materials. Of course, that is also known as the mechanics of solids, and this particular equation, bending equation, is very important from gate examination point of view, as well as your conventional examination, especially a long answer question type of questions. It is very important. Now, any derivation, remember that it is valid only under certain assumptions. So, we are going to list out the assumptions which are applicable to bending equation. So, these assumptions are, the very first one is loading is done within the elastic limits. I am calling it as within the elastic limits. That means the moment you withdraw loads, it must completely regain its initial shape and size. That is what is elastic limits. And second assumption is here, as you know, when the beam is loaded, it is going to bend like a bow about the neutral axis. The stresses either of the side, it will be tensile and compressive. If we select a simply supported beam, it is the topmost layer will be undergo compressive and bottom will be under tension. And if you select a cantilever beam, it is the top will be under tensile stress and the bottom will be under compression. So, depending upon the type of the beam, either of the side of the neutral axis, the fibers, the layers will undergo tensile as well as compressive stresses, and E is that is Young's modulus, E, or you can call it as even Y also, is a constant. I am calling it as a constant, means it is same in tension as well as in compression. This is your second assumption. And the third assumption is here the material is assumed to be homogeneous. The material is homogeneous. That means it is a single material. And the fourth one is isotropic. The material is showing the properties in all the directions, same properties, and that property is called isotropic. The material behaves isotropic, that means the properties in all the directions are same, and these four are generic in nature. And fifth one, let us see that when a beam is subjected to bending, the radius of curvature, I am representing radius of curvature as rho, is very large, when compared with its length of the beam. So, that means it is the deflections are very small. When radius of curvature is large, means the deflections are very small, and this is indicates that deflections level, that is deformations and deflections, are very small. And the next assumption is when a beam is bent, here the before the loading and after the loading, the plane remains same, in the same plane. That means if it is the perpendicular to the axis, a plane perpendicular to the axis, before the loading and after the loading, it is remains in the same plane, and that it is called here the plane, the material the plane is plane remains same. I am calling it as a plane remains same. That means that before bending and after bending, if we consider perpendicular to the axis, that remains same. And lastly, and the very important assumption in this is pure bending. It is pure bending. The beam is assumed to be undergoing pure bending. So, this property we have to discuss in detail about the pure bending. That pure bending is nothing but it is without shear force, and this particular condition is only applicable. Let us consider a beam, a simply supported beam. I am calling it as simply supported. At end A you have a roller support RA, and end B a roller support RB, and which is loaded with external force P at a distance A from the left end, and same load, that is P, at a distance A from the right end, and the length of the beam is L, or the span of the beam is L. So, this is the given beam which is loaded 2 point loads at equal distance. So, if you draw the shear force diagram, if you draw the neutral axis, This is what I am representing as the neutral axis. NA stands for neutral axis, and as you know that it is a positive shear force. You have up to this it is a positive shear force, and here it is a negative shear force of magnitude is equals to that RA and RB also. It is because of the symmetry, both are equal, and this level is P and this level is also P, and this is plus shear force, positive shear force and negative shear force. Let us mark this as CD. This length is CD. Observe carefully, there is no shear force between C and D, and if you draw the bend moment diagram for the same, so let us draw with the same alignment, and let us consider again the neutral axis NA, and if you see that it is the load is continuously increasing, it increases to it is P into A and remains constant, and again you will get that means the total bending moment diagram is it is P into A. This is the value of this, and it is positive. So this portion, this particular portion, remember that this portion is called pure bending. You have only bending moment. It is something like, you know, pure milk without water. It is pure bending without shear force. Only bending without shear force is called pure bending, and that is one of the important assumption. Now let us consider the deflection, and let us select at a distance x from the left hand an elemental length, I am calling it as dx. Let us draw this dx, magnified view of the diagram of the dx, the beam having certain cross section, maybe a rectangular or any cross section, and let us analyze in detail about this particular elemental length dx in order to derive the expression for the bending equation, that is what is known as flexure formula. Here now the magnified view of this, let me draw. Here I am considering significant cross section. This length let me call it is dx. It is a magnified view of the element, and somewhere here you have a neutral axis, and this length I am calling it as AB, and the bottom at a distance y from the neutral axis. This is what is the neutral axis, NA. So this distance is y. So this is before bending, before application of the loads. Now once it is deflected, and assume that it is, if you draw a tangent and a normal to it, and a tangent and normal to it, this include angle, let us call it is d theta, and the radius of curvature is rho, and this arc length dx is equals to, you can write down, it is arc length dx is equals to, it is rho into d theta, or it is rho is equals to, it is dx by d theta. This is one expression from the beam diagram. From here you have just written that it is arc length. Arc length is equals to rho into d theta. That is what is your dx. And after this, let us, this is what is your magnified view. Now, once it is loaded, then what happens? You can see that it is bending like this. You can see that it is the constant radius of curvature, and somewhere you have neutral axis, and let me take this is your element, and at neutral axis it is AB, and which is also equal to your dx. AB is equals to dx, right? And if you extend it, somewhere you have d theta, and it is rho, and this here at a distance y you have the element, that is you call it as element as a CD, element as a CD. I am calling it as a CD. Now it is after expansion, it is I am calling it as CD, and let us draw a parallel to this passing through this neutral axis. This is parallel. So, obviously, this point I am calling it as D prime. D prime. Observe that when it is loaded, it bends like a bow, and let us analyze in detail about this particular layer which is having a cross section area dA at a distance of y from the neutral axis. This distance is y. Now, let us observe that before loading it is a dx, that is equals to AB, which is also equal to your CD also, both are equal. Once it is loaded, it bends, and this particular layer CD will undergo extension, it is going to expand. So, how much it is extended? It is D prime D is the extension, and this is again d theta, this angle is d theta, and you can write down this angle d theta, or it is D prime D is equals to, that arc length is equals to y into d theta, y into d theta, and you can write down d prime is nothing but it is extension, and if you write the expression for the strain, I am using a symbol epsilon. Strain is equals to, it is d prime, and d prime value is y into d theta divided by the initial length, that is AB, or which is also is equals to CD prime, and that is nothing but your dx. I am writing it as dx. So, you can replace dx by d theta with rho. So, this becomes y divided by, it is rho, y divided by rho. But as you know that from the basic definition of a strain, it is stress by Young's modulus. Stress by Young's modulus is it is y by rho, and from this equation you can write down expression for the stress, that is E into y by rho. So, let us substitute this and write the expression for the elemental moment, that is dm. Dm is equals to, it is the force, that is sigma into, it is elemental area dA, but sigma value, it is y E into y by rho into dA, but it is at a distance distance y. You have another y, that becomes y square, and as you know that total moment m is equals to integral of, you can write down E by rho is outside, integral y square dA, and integral y square dA is nothing but I. So, this particular term you can rewrite as somewhere here I am writing, let us look at this, it is m is equals to, it is E by rho into I, where I is the moment of inertia, or it is m by I is equals to, it is E by rho. So, this is one equation, call it as equation 1, and rewrite this equation. Here it is sigma by, or it is E by, it is E by rho is equals to sigma by y. So, here sigma by y. Another equation is from this, it is sigma by y is equals to, it is E by rho. This is your equation 2. From equation 1 and 2 you can conclude that it is m by I is equals to, it is sigma by y is equals to E by rho. This is what is your required bending equation. Here if look at the terms, it is ma is bending moment or bending resistance, and I is the centroidal moment of inertia, and sigma is the stress, maybe tensile or compressive, and y is the distance from the neutral axis, and E is the modulus of elasticity, and of course it is Young's modulus, and rho is the radius of curvature, and these are the definition of the terms, and you can make use of this particular equation in order to design the beams. I hope you understood this particular derivation. Thank you very much for watching this video.